We are very happy today to have with us Jon Sorce. He will from MIT, and he will tell us about analyticity and the Unruh effects. Please.
Great. Great to be in Chicago. Great to see you all. I'm here all week, and I look forward to chatting with all of you. So this talk today is about something called modular flow. That's the big picture. Modular flow is something that has really grown in popularity over the past 10 years as a tool for understanding and exploring quantum field theory. But it's something that I think hasn't had a huge amount of buy-in from the community as a whole, because it is notoriously a very finicky and difficult tool to deal with, despite its sort of incredible usefulness. And what I'm going to be talking about are two papers here, which are sort of trying to set the record straight and make this tool of modular flow accessible to everyone and useful to everyone for actually understanding quantum field theory. So because I'm talking about something which, as I've just said, has a little bit of a technical history to it, I'm going to focus in this talk a lot on sort of motivations and big picture ideas. I'll talk a little bit about technical results, but the goal is for everyone to walk out feeling like they know what modular flow is and what it's good for and what some of its applications are, not necessarily knowing all of the finicky details. So here, okay, so here's my summary, or at least one very big picture summary. If there's only one slide you take away, it should be this one. The thing that we're trying to understand is the sort of fact, the empirical fact, that quantum field theory often exhibits thermal behavior in settings that naively looked out of equilibrium. Some famous examples that we'll talk about more throughout this talk are, for example, black hole radiance, for example, the Unruh effect in Minkowski spacetime, or for example, the generalized second law of black holes with semi-classical quantum matter. All of these are settings where you have just sort of some quantum fields propagating in spacetime that you set up in a particular way, and you find that if you look at them from a certain angle, they start to look thermal, and you start to see an emergence of thermal physics. The modern language for talking about emergent thermal physics is the language of modular flow. These are one and the same, and over the course of this talk, I'm going to try to convince you of that and explain sort of how to think about what this bolded term actually means. But the point of it, its job in life, is to help you unify your understanding of these kinds of emergent thermodynamics. And consequently, because it's a mathematical tool that helps you unify your understanding of these things, it's also a tool you can use to prove general structural statements about quantum field theory. I'll talk more about these applications in a few slides, but some places it's showed up are Aaron Wall's proof of the generalized second law, Tom Faulkner and collaborators' proof of the average null energy condition, and some interesting work that many people, myself included, have been contributing to, thinking about entropy and semi-classical gravity. So we'll revisit these in a few slides. But the big picture I want to drive home is that the general theory of modular flow in quantum field theory is incomplete, and our ability to make progress has been seriously limited by this. And there's an ongoing program, part of which is going to be presented in this talk, to try to fill this lacuna and understand this technology better. So here's the outline of the talk. These first two are probably going to take up the majority of the talk. I'm going to start with some history and motivation, be a little more explicit about what I mean by emergent thermodynamics in quantum field theory, and explain a little bit more about these applications that I indicated on the previous slide. Then I'm going to give you an introduction to modular flow, and I'm going to present it in a way that I think is fairly novel as compared to previous presentations. It's based on this paper that I wrote last year, where I'm going to try to introduce you to modular flow as I indicated previously, the unique mathematical tool that's available to you when you want to understand thermality in quantum field theory. Then we'll go and start talking about this new paper that I wrote about a month ago, which is providing general constraints on local modular flow. I'll explain what those words mean later in quantum field theory and how they sort of set the boundaries for what we expect to be able to do with this technology in terms of understanding quantum field theory. And finally, I'll comment on ongoing work. So everything that we're talking about here starts with black hole radiance. Starts with the observation that collapsing black holes tend to dynamically radiate thermal radiation. And the way this is originally formulated is in sort of an S-matrixy language. You do quantum field theory in curved spacetime, where the spacetime that you're doing the quantum field theory in is a spacetime describing a collapsing black hole. And what you find, if you try to compute some sort of scattering process, is that a state that goes in as the Minkowski vacuum comes out as a thermal state. And you just find this, for example, by solving the free field equation in this background and just seeing what happens to the solutions of the wave equation as they propagate. So this was understood in 1975, and almost immediately afterwards, Bill Unruh observed that there's something sort of qualitatively similar, but conceptually different, that happens even in the Minkowski vacuum. And this is what's called the Unruh effect. And he observes that accelerating observers experience the Minkowski vacuum as a thermal bath. So here's our space-time diagram of a Rindler decomposition of Minkowski space-time, and here's a family of boost trajectories in the Rindler wedge. And what Unruh tells us is that sort of a detector traveling along one of these trajectories is going to view the vacuum state as though it was a thermal state. There's a very interesting thing that's happened in our language when we move from the previous slide to this one, which is that we started talking about something where we're not talking about a dynamical process for the quantum fields. We're talking about a stationary state of quantum fields that is being probed dynamically. And somehow it's the dynamics of the probe that are causing this emergence of thermal behavior. You can map this back to black holes. And this was used in sort of a general argument for black hole radiance in interacting field theories, where you think about the eternal Schwarzschild solution. And it just so happens that the eternal Schwarzschild solution has a natural vacuum state, which has the property that it looks thermal to Schwarzschild observers following these Schwarzschild time trajectories. So it's like the Unruh effect, but it's in a different space-time background with a different state. It's an avatar of dynamical black hole radiance, but strictly speaking, it's a different phenomenon because it involves this stationary state and this dynamical probe. So, as I said, in both versions, we have a state of a phenomenon where a quantum field theory looks thermal, quantum field theory state begins to look thermal when you probe it in a particular way. This is something that many of us learn in grad school, but I think is still worth being amazed by. It's a deep statement about the structure of quantum fields, and it's something you can use to organize your thinking, for example, about the entanglement structure of the Minkowski vacuum. And a question I want to ask, partially for conceptual interest, is how special are these examples? I've just given you two examples of situations where there's a space-time with a particular quantum field theory state that begins to look thermal when you look at it in a particular way. And I want to know how many more examples there are. And something I'm going to try to emphasize as we go on is that this question has really not previously been understood in any kind of generality. Now, I'm going to begin to use this terminology, which will be explained in a few slides. I'm going to describe such states, these states that generalize the Unruh effect, as states with local modular flow. Those words are maybe not suggestive of anything. For the moment, you can just take them literally as substitution for states with a generalized Unruh effect. But I'm going to claim in a couple of slides that this is the best way to think about this phenomenon. All right. So I've told you that I want to ask about generalizations of this phenomenon. And what I'm going to tell you first is that there are so few known examples of this phenomenon that I can fit them all on a single slide. In fact, pretty much every known example is related to the two I've already discussed, the Minkowski vacuum and the Schwarzschild black hole, by a conformal transformation or by a change of the cosmological constant. So one typical example is a conformal field theory vacuum in a causal diamond. If you draw some causal diamond in Minkowski spacetime, there's a conformal isometry of this diamond that preserves it, that sort of goes forward in time. And if you were to send a detector along one of those trajectories, it would experience a CFT vacuum, not a general QFT vacuum, it would have to be a CFT vacuum as a thermal state. Well, this shouldn't surprise you because the causal diamond in Minkowski spacetime is related to the Rindler wedge by a conformal transformation that brings infinity into finite distance. So if I do that transformation and I'm in a conformal field theory, then there should be an avatar of the Unruh effect in this particular case. And in fact, all of the other examples we know of this kind of generalized Unruh effect happening are black hole examples in de Sitter or anti-de Sitter instead of in asymptotically flat spacetime. Analogs of Rindler wedges in de Sitter or anti-de Sitter spacetimes, analogs of causal diamonds in the CFT case for de Sitter or anti-de Sitter spacetimes. All of these three examples fit under the setting of static killing horizons. And there is one additional example in 2D CFT that's a little bit special that comes from the chiral factorization of the two copies of the Virasoro algebra. It would take more time to describe, and I won't describe it. I'm just mentioning it to tell you that there's really only one other known example of this phenomenon occurring. So that's the history of these states. But now I want to tell you a little bit about the applications of these states. And in particular, I want to tell you that the reason I'm asking this question about when this phenomenon can happen is not just that I think it's cool or interesting. I mean, I do think it's cool and interesting to understand these things about quantum field theory. But it's also true that states with this property, this local modular flow, this kind of generalized Unruh effect, are extremely useful in applications. I'm going to list some of the applications on the next slide, and I'm not going to talk very much about them, but I want to at least give you a flavor of why you might expect that such things would be possible. The point is that when you have a family of observers sort of propagating in a space-time and probing a quantum field theory state, they're going to couple to that quantum field theory state via a Hamiltonian that can be expressed as some integral of the stress tensor of the quantum field theory. And that integral is going to, be an integral against a particular vector field describing the trajectories that they take. And then, if you have a Hamiltonian that is describing such a family of observers, and if you have one of these states with a generalized Unruh effect, so there's a thermal relationship between this Hamiltonian and a particular quantum field theory state, well, then you can use general principles coming basically from statistical mechanics, to derive universal properties of the stress tensor just by making these two things talk to each other. So what can you actually do with this if you sit down and try to understand it? Well, here are some really great examples. I think this work really got underway in this work by Cassini and collaborators, understanding renormalization monotonicity theorems in quantum field theory. So that's the C theorem in 2 dimensions and the A theorem in 4 dimensions. So these are theorems that track what happens to the anomaly coefficients of a stress tensor under a renormalization trajectory. And the way that they argued for this, using entropic ideas, was to use this fact that I mentioned before, that there's a generalized Unruh effect for the CFT vacuum in a causal diamond. That gives you some relationship between sort of the thermal data of the vacuum restricted to this sphere and the stress energy tensor of the theory. And indeed, you can make these two things talk to each other and extract a renormalization monotonicity theorem out of it. Similar kinds of arguments show up in Wall's paper about the generalized second law in semi-classical gravity, where if you want to prove a generalized second law, you need some relationship between matter entropy and black hole area. Well, matter entropy, that's some sort of thermal property of a state. And area, that's going to be related to the stress tensor of the matter via back reaction. How do you make those things talk to each other? You use this kind of local modular flow. And indeed, what Aaron did was he used the local modular flow for this so-called Hartle-Hawking state of a static black hole. There's also work proving general energy conditions in field theory, these average null energy condition and quantum null energy condition. That uses this local modular flow of the Minkowski vacuum and Rindler wedge. And finally, something that I've been working on recently with some, I've been working on with people and also many authors, including Witten, Chandrasekaran, Pennington, many others have worked on, is trying to understand entropy of black holes in semi-classical gravity. And this again uses the local modular flow property, not just for black holes, but for a general static killing horizon. Yes?
The sub-bullet talks about modular flow of the CFT. How is that going to be mapped to a C theorem?
A C theorem, because when you look at, that's right.
C conformal theorem.
So if you have a renormalization group trajectory that looks like a CFT fixed point in the UV and a CFT fixed point in the IR, then what you expect, or in fact you can argue for, is that if you look at the entropy of a very small subregion, that's going to be governed by the UV anomaly coefficients, and for a very large region, by the IR anomaly coefficients. And so then these things are related to each other in the interacting theory by some entropic principle. Okay. So these applications are really cool, something that I got really excited about starting when I was a grad student and continue to be excited about today. But one thing I want to emphasize is that the applications are not particularly unified. What happens in these cases is that we sort of get lucky. We have a state with this nice generalized Unruh effect, and then we play around with it and we end up deriving some interesting structural feature. And I think, at least from my understanding of this subject, it feels important to develop some kind of general theory of these generalized Unruh effects, these local modular flows, in order to understand how far this technology can be pushed. One reason I think this is really important is, for example, in this paper, which I won't talk about the details of, we pointed out that there are cases where you might have thought you needed one of these generalized Unruh effects, one of these local modular flows, but you can in fact get away with things that are a little bit weaker and perhaps a little bit more general. And this is still sort of fitting into a piecemeal understanding that we've developed so far. And it seems like it's a fruitful time to understand this general theory in order to be able to put everything together into a coherent and compelling way. That's everything I wanted to say about the applications. And now we're going to get into the sort of more technical material of the talk, and I'm going to tell you what modular flow actually is. Any questions about the first part before we continue? Now's a natural pause. Okay. So I've asked a question, which was a physicsy question. When does something like the Unruh effect happen? In order to answer that, I need to tell you what the rules are for answering it. I need to give you some precise mathematical definition of the thing that I'm trying to prove. So we need a definition of what it means for a field theory state to look thermal. Now, the way Unruh originally formulates this is in terms of particle detectors. He says if you take a two-level system and you couple it to a quantum field theory vacuum in a particular way and you send it along a particular trajectory, it's going to start clicking, detecting particles with thermal statistics. This formulation is not particularly robust in terms of being able to manipulate it mathematically. And there is a more robust formulation, which is in this language of modular flow. It's a very simple idea. And it starts with thinking about statistical mechanics. So often what you do when you do statistical mechanics is you have some Hamiltonian that you want to understand. Perhaps it's a nearest neighbor Hamiltonian on a lattice. And you, instead of trying to understand the Hamiltonian directly, you try to understand its thermal ensembles. These density matrices that are proportional to e to the minus beta h. So they encode the Boltzmann distribution. And indeed, when you do statistical mechanics, you largely just try to study the properties of these states or of generalizations to grand canonical ensembles or ensembles with other kinds of chemical potentials or so on. But there's a converse thing you can do, which is instead of starting with the Hamiltonian, you can start with the state. And given a density matrix, you can always just formally write it as rho equals e to the minus log rho, and identify that minus log rho as some operator k. So this is an expression that sort of looks like the expression for a Gibbs state. And indeed, if you think about what are the properties of this operator k, well, rho is a density matrix, so it's bounded below by 0 and above by 1. When you take the logarithm and you take a minus sign, what you find is that this operator k is Hermitian, and it's bounded below, but potentially unbounded above. So at least at the mathematical level, you could reasonably call it a Hamiltonian. The caveat is that typically it's not going to look anything like the Hamiltonians we usually like to study. It won't look local with respect to the lattice structure that you defined your state on, for example. But you can still, at least just for organizing your thinking, you could treat it like a Hamiltonian, and you could call it something. It's called the modular Hamiltonian. The word modular is a historical accident. Don't think too much about it. It's called the modular Hamiltonian, and you can try to understand the state using the tools of statistical mechanics applied to this rather unusual Hamiltonian. And in fact, this is one way, and in fact, my preferred way, of thinking about what quantum information theory does at the core. It tells you that you can study general states by using the ideas of statistical mechanics, by treating them as thermal with respect to this funny notion of Hamiltonian. Now, this gives us a little bit of a flavor of the question we're trying to ask sharply in quantum field theory. We're sort of trying to ask something like the following. Given a density matrix for a quantum field theory state in a particular region of spacetime, when does the associated modular Hamiltonian generate a local transformation of fields? Right? The modular Hamiltonian is the thing it looks thermal with respect to. Is that thing going to look like something local in the theory? That's the question we're asking. This is a good way of orienting your thinking, but it's very, very hard to make progress with this formulation of the problem. The reason is that in quantum field theory, density matrices are UV divergent. So if you want to deal with density matrices at all, you need to put in some UV cutoff, and you need to deal with the UV cutoff and treat it very carefully. In fact, this modular Hamiltonian involves a logarithm of a density matrix. So you're taking a logarithm of a UV divergent quantity, and that's going to be even harder to deal with. So typically, it's easiest to approach a question like this by reformulating your question in a language that already makes sense in the continuum, so you don't need to worry about these UV divergences. Well, the easiest objects to study in quantum field theory are correlation functions of local operators. So what we'd like to do is re-express this idea of the modular Hamiltonian in a correlator first language. And this is exactly what's done with this thing called the KMS condition. KMS condition is something that, sounds kind of technical, but is actually quite a simple idea. It just sort of says, let me think about what thermal physics means for correlators. So what you do is you think about the 2-point correlation functions in a particular density matrix, and you evolve that correlation function with respect to this funny notion of modular time, this funny Hamiltonian that came from the density matrix. So you look at the expectation value, A and B are just two general operators. You look at A of S times B, expectation value in rho, and what that means is this expression here, trace of rho times either the IKSA, either minus IKSB. And if you just plug in this expression for the modular Hamiltonian, rho equals e to the minus k, you can rewrite it as follows. And the question that Kubo, Martin, and Schwinger asked, that's what KMS stands for, about this correlation function, is when can this be analytically continued in S? And you have to do a little bit of math to figure out the answer to this question in any kind of sharp way, but your intuition is actually going to be the correct thing. K is some operator that's bounded below but not above. I'm taking some exponentials, so I only really expect the expression to make sense if both of the exponentials are decaying rather than growing. So what that means is that for the first exponential to make sense, I need the real part of is minus 1 to be non-positive. And for the second exponential to make sense, I need the real part of minus is to be non-positive. Indeed, if you do a little bit of math, you can show that this intuition is correct, and that if you restrict to the domain where both of these inequalities are satisfied, this is in fact an analytic function of S. And what that domain looks like is very simple. It's a strip in the complex S plane where the imaginary part is smaller than 0 and bigger than minus 1. So that domain looks like this. You have some strip in the complex plane whose top boundary is S and whose bottom boundary is minus I plus S. And there's some analytic function in there that reduces to our original correlator on the top boundary. And in fact, it even does something simple on the bottom boundary. You can see this by plugging in minus I plus S into this expression up here. The minus I moves the density matrix around, you use cyclicity of the trace, you shuffle everything around, and what you find is that all that happens is that the order of the operators in the correlator gets switched. So this is just an interesting feature of correlation functions in thermal states. It's what's called the KMS condition, the fact that they admit an analytic continuation that looks like this. Now, the reason that we bother to define this is because it gives us a way to define what we mean in the continuum for a state to be thermal with respect to a particular notion of time evolution. And we can do this without making any explicit reference to a density matrix. So what we're going to do is we're going to say, by analogy with Gibbs states in quantum mechanics, we're just going to declare that what we mean by a state of quantum field theory looking thermal in a subsystem with respect to a time evolution map is that all of the correlators of operators in that subsystem have the appropriate analytic structure. These 2-point functions that you time evolved can be continued in a way that looks exactly like the diagram on this slide. All right. So this is going to give us a definition. And we're going to argue in a second about whether or not this is a good definition from the perspective of physics. Whether it's a good definition from the perspective of math can't really be debated because it's just a definition. We're going to say what it means for a state to be thermal in a subsystem with respect to a Hamiltonian. Before we look at the conditions, I want to say there's a little bit of sleight of hand, which is that you can't directly export the expression that I wrote here to a general setting, because even though I can talk about this correlation function without mentioning the density matrix, somehow sort of because the density matrix doesn't make sense in all settings, it's UV divergent in the continuum, what I really want to do is rewrite this expression in a way that deals with the purification of the density matrix. It's easy to see what that's going to do on the left-hand side. You're going to be taking an expectation value in some pure state that purifies the density matrix. The only thing that's going to change on the right-hand side is that this modular Hamiltonian was like a one-sided operator that only acted in this system where the density matrix was defined. You're going to need to add a little piece to it that acts in an appropriate complementary way on the purifying system. Yes?
So what do you do with the zeros of the singular value decomposition of rho? Like
Of rho?
Yeah. When you
Good. So that's something I didn't say. This does not work when rho has 0 eigenvalues. So this actually only works for full rank states, right? When you have a non-full rank state, you can still do things like this, but you have an ambiguity that you have to resolve, as you say, exactly in the sector of 0 eigenvalues.
So do you like quotient or something, or do you get rid of it?
Usually you just put the identity there and you ignore everything.
Okay.
You just say you're only going to worry about what happens in the sector of Hilbert space away from the 0 eigenvalues. Okay. But yeah, so in fact, when I wrote this expression, secretly I was assuming that rho was full rank so that the logarithm was well defined.
Yeah.
And that'll show up again in a moment on the slide immediately after this one. But let's say our definition. we're going to declare. And before you even look at the definition, you should think in your head, the typical example is going to be Minkowski vacuum, Rindler wedge, boosts, because that's the Unruh effect. So a state is thermal in a subsystem with respect to a given Hamiltonian if the time evolution corresponding to this Hamiltonian preserves the state, if it preserves the operators in the subsystem, something that starts in the subsystem ends up in the subsystem, and if the time evolved correlation functions for AB operators in the subsystem have this nice analytic structure we talked about before. Okay, so this is certainly true for the Unruh case. Boost time evolution preserves the vacuum state. Boosts keep the Rindler wedge mapped into the Rindler wedge. And it is true that 2-point functions evolved with respect to boost time admit a KMS analytic continuation. Okay. So this is a definition. And now we have to ask if it's a good physical definition of what it means for something to be thermal. Does it capture what we wanted from thermal physics? And I claim the answer is yes. And the way to see this is due to a very general theorem from the operator algebras literature. So these were mathematicians who were asking a very different kind of question. What they said was that if you think about a state and a subsystem, such that the state is sufficiently entangled between the subsystem and its complement, there's a technical condition, the state is so-called separating. It's exactly the continuum version of a state being full rank. So of course you sort of need that to exist in your continuum version of the theory. It typically is satisfied in quantum field theory, so don't worry about it too much. If your state is sufficiently entangled between your subsystem and its complement, and the subsystem is represented by a von Neumann algebra, that's some technical mathematical object that organizes the way you think about operators in quantum field theory. Again, these typically exist in quantum field theory, so you don't need to worry about that assumption so much. The conclusion of this theorem is that a thermal Hamiltonian exists and is unique. So let's think about that for a second. Existence is kind of miraculous. I don't know if I would have expected it to be true. It tells you that every sufficiently entangled quantum field theory state in any spacetime region looks thermal with respect to some funny time evolution map. But much like the modular Hamiltonians of lattice systems, this thing won't generally look like something nice and local. It'll just be some funny Hermitian operator. But actually, for our purposes, uniqueness is the important thing. Because all we wanted to know was whether or not we had picked a good definition of thermality in the continuum. We took one property that was satisfied by thermal states on the lattice and we exported it to the continuum. If we know that we have a unique structure coming out of this, then our definition is good enough. We couldn't have picked anything else that would have restricted this definition further. We are necessarily capturing everything important we wanted. All right. So that's the justification for why we should think about this KMS condition.
Question.
Yes.
So just to make sure I understand, so if you have, let's take vacuum state or any state, and you pick a subregion, look at the reduced density matrix there, and log of that would produce this K.
Mhm.
Right. So if I'm not too worried about UV divergences and
Then you might not,
rigorous,
then existence might not surprise you.
Right.
Right? I completely agree. Yeah. Well, the thing that we're talking about, maybe I should say, is log of rho on this subsystem minus log of rho on the other subsystem, because it's a two-sided operator, right? And so I guess the thing you might worry about is whether like the UV divergences and those things are well enough behaved with respect to each other that this operator makes sense. And maybe you don't worry about that, and then this existence is totally obviously true.
and so for the actual rigorous proof, so rho doesn't quite exist, but K exists. Is that roughly the
Yeah,
same?
that's right. That's right. Yeah, you sort of think of K, the log rho minus log rho, canceling the UV divergences. That's right. So let me make a quick comment on this theorem. It's a really hard theorem to prove. A mathematician who I talked to said that it was first described to him as, he said his advisor said, now we have the following miracle, and wrote down the statement of the theorem. But one thing I want to emphasize is that in this theorem, it actually turns out that the existence part is what's hard. That's where all the heavy lifting happens. And one thing I showed in this paper from last year is that you can actually prove the uniqueness part without knowing the existence part and using a proof that relies on very simple physical ideas. So, I'm happy to explain that later if anyone's curious, but the point of this is that you conclude that it's not so hard mathematically to see that this gives a good definition of thermality in QFT, because for that, all you needed was the uniqueness. If you want to understand the existence, I did also give a new proof of that in this paper that might be a little bit easier to understand for physicists than the math proofs, but it still is quite technical, so I don't recommend looking at it unless you want to be an expert. All right. So now that we've talked about this KMS condition, and we've said that for a given state that, has sufficient entanglement, blah, blah. Because this thermal time evolution Hamiltonian is unique when it exists, we're allowed to give it a name, and we're allowed to call it the modular Hamiltonian in the subsystem. And the unitary group that it generates is called modular flow. So if we recall the question we started asking in quantum field theory, and we called the applications, we're going to be thinking that heuristically, we should think of a state with local modular flow as one where the modular Hamiltonian is written as some integral of the stress tensor over a spatial slice. And the way that all of these applications work is that you say, well, I know that I have this KMS property, and that gives me some analytic continuation of correlation functions that seriously constrains the structure of this operator K. And then you can translate that into constraints on the structure of the stress energy tensor. And that gives you all of these applications. Thinking in that language is what gives you all of these applications of local modular flow.
Just the stress tensor or also the vector field?
Good, so the vector field, actually, in a way, what we're talking about in the rest of the talk is what the constraints on the vector field are. But a particular state will have a particular vector field, right? But the sort of, let me see how I want to say this. If I have a local modular flow, then there is going to be some integral like this. The modular Hamiltonian can be written as the integral of the stress tensor dotted into a vector field. And yeah, I guess what you really get from the information about K is some information about how the stress tensor relates to this vector field. And that's something that you can draw conclusions from.
Something where the vector field's going to have some sort of symmetry property.
Yes.
Yeah.
That's what the general constraints on local modular flow are.
But does the left-hand side depend on the vector fields? Because I have the vector field on
Okay,
the
good.
right-hand side.
So depend is-
On the other hand is unique.
Yeah,
So-
good. So if I have a state with, here's the precise statement you should think about, or this isn't even precise but the way you should think about this is if I have one of these local Ks, then there will exist some vector field
Okay.
such that an integral like this exists. So what we're about to talk about is the question of what kinds of vector fields could show up. But what I wanted to emphasize here was just that the fact that there will exist a vector field such that if you have a vector field such that there's a relationship like this, that will give you information about the stress tensor. So that's why this is a useful tool.
But so far, no one guarantees there is such a vector field.
You have specific examples.
Okay,
That's right.
but you haven't yet implied by all these theorems.
No, that's right. And in most cases, there will not exist such a vector
Okay.
field.
You started off giving a list of known examples, so this is sort of like general approach going to give you an enlarged list of examples, or you're going to just find the known examples in a fancier language?
Mostly, no. What I'm going to do, I don't think either of those things. What I'm going to do, there will be a few more examples, but not very many. And that's the thing that's sort of interesting about this, is it is emphasizing the limitations here, but also I think it's going to suggest for us how we want to go beyond those limitations. And that's what I'll talk about at the end. Okay, so that's the next part of this talk. As you've anticipated, it looks very special that you might have an equation like this, and indeed it is, and we're going to seriously constrain when this can happen. So what this paper does is it proves two theorems of the following kind in quantum field theory for these modular flows. If modular flow is local, then X. Obviously, having theorems like this is useful because it lets us constrain when it's possible for local modular flow to arrive. If we don't have X, then we don't have local modular flow, right? And therefore, as I just indicated in the answer to Emil's question, we're going to be able to talk about when we expect to be able to use this technology to understand UFT. So the two theorems that show up in this paper are seriously constraining. The first theorem, as Emil already anticipated, is that there's a symmetry consideration. If you have a local modular flow, the diffeomorphism it implements has to be a conformal symmetry of spacetime. This is seriously constraining. Most spacetimes don't have any conformal symmetries. And in part, you might hope that, I just say, well, okay, too bad, but this does at least explain why there were so few examples. The second theorem is actually the one that I think is more interesting, even though it's less constraining. because it has more to do with the actual structure of these modular flows. When you have one of these local modular flows and some additional technical conditions, the diffeomorphism that it implements has to be future directed. That's kind of funny. We'll talk a little bit more about that as we go on. But let me at least flash for you some things that are getting ruled out.
Question.
Yes.
Well, actually, related to theorem one.
Oh.
So one might be interested in the context of quantum field theories that are not.
Non-relativistic.
Exactly.
This
So
is
does
all
that
for
feel-
relativistic field theories. Non-relativistic field theories are unconstrained.
Or what's again?
Not constrained, because the key tool in both of these theorems is the assumption of microcausality.
Mhm.
So if you don't have microcausality, like if you don't have sharp light cones, then you don't have either of these theorems.
I see. So this doesn't necessarily disprove, or it means that there's still hope for local modular Hamiltonians in non.
In the labs. Yeah, that's right. Yeah, that's right. In higher derivative theories that you might use for effective models of anything, like, yeah. And I think that would be great to understand. It's just that this is where I could make progress. So this first theorem is going to rule out, completely arbitrary flows that don't look like any kind of symmetry of spacetime. But there are additional things that are ruled out by theorem 2. For example, if you think about dilatation of a Rindler wedge, that is a perfectly good conformal symmetry of Minkowski spacetime, and it preserves the Rindler wedge. But I'm going to tell you that these things can't actually arise as modular flows. And the fact that they can't arise is sort of interesting. It tells you something about the structure here that's happening, I think, in a compelling way. So let me give you an outline of theorem 1. The argument's very simple. You start with microcausality. And in fact, microcausality is the key player in both of these proofs. I'm going to write everything for a single scalar field for simplicity, although you can formulate this for arbitrary theories. I'm going to start with the assumption that I have a scalar field and that at space-like separated points, it commutes with itself. And what I mean by a modular flow being local is that if I have one of these modular Hamiltonians K, then what it should do when I act on the field operator with it is it should send it to a field operator at a different point in space-time that's related to the first point by some group of diffeomorphisms. I've written a tilde here instead of an equals to just sort of remind you that if this had some spin or some non-trivial scaling dimension, there might be some linear transformation here as well, in addition to the sort of moving of the space-time point. But we'll forget about that because we're thinking about a real scalar field. The conclusion you draw is that if you have space-like separated points, then the commutator vanishes. So the modular flowed commutator vanishes. And if you move the modular flow inside the commutator, you find that the commutator of these transformed field operators will still have to vanish. If modular flow were not local, this would not be very constraining. If you give me some crazy non-local combinations of field operators, then they might commute or they might not commute. That's going to have some delicate dependence on the detail of the non-locality. But if I have two local operators, then whether they commute or not really just depends on where they are in spacetime. So local modular flow can never take space-like separated points to point separations where fields do not commute. That's the conclusion of this. You have to think about this a little bit carefully to think about all of the different kinds of field content that you could have in a theory, but the basic idea is the right one, which is that you think this through and you find that if local modular flow implements a group of diffeomorphisms, then those diffs must take space-like separated points to space-like separated points. In other words, local modular flow always preserves the causal structure of spacetime. Now, one thing you might know is that conformal symmetries preserve causal structure. That's one of the key features of conformal symmetries. So certainly, conformal isometries are candidates for local modular flow, at least within the framework of the stuff that we've already ruled out. So now let's just ask a geometry question. Are there any others? Does space-like to space-like imply conformal? Now, if you have a question like this, there's a really efficient algorithm for answering it, which is you send an email to Bob Walt, and you ask him, do you happen to know if the following statement is true? If a diffeomorphism of a Lorentzian manifold preserves causal structure, then it must be a conformal isometry. Okay, this was over a year ago. I emailed Bob at 9:11 a.m. He emailed me 27 minutes later. This was Boston time, by the way. So this was 8:11 a.m. Chicago time. He emails me 27 minutes later. He says yes. And he also tells me that he found the answer on Google. So maybe I didn't try hard enough before emailing him. He did give me exactly the paper that I needed to understand. Okay, so you need to do a little bit of work to fit all of these things together, but the conclusion is solid. In quantum field theory, every local modular flow is a conformal symmetry of spacetime. And as I emphasized before, this is going to at least give us some context for why we have these dearth of examples and why these examples that we showed up were already so hard to find. It's not as good as finding a lot more examples, but at least we understand what's going on a little bit better. All right. So as I emphasized before, there's additional stuff that we might want to rule out. For example, these conformal symmetries that are not future directed, we're going to be able to rule them out under some additional assumptions. So this is like a dilatation of the Rindler wedge. I'm going to argue that there's not going to be any good state that has this as its local modular flow.
So
Yes.
you're not excluding past directed like ones.
I am excluding past directed.
Oh, okay.
There is yes, past directed cannot happen. In the kinds of states I'm going to discuss, there's some technical assumptions. Okay. But this is an interpretation. It says that every one of these generalized Unruh effects can be probed by a physical family of observers. People actually propagating causally in space-time would be able to measure these things.
In the context of entanglement, there it's null, I guess, or
In context of entanglement, what?
when you look at the reduced Hamiltonian on half space.
Uh-huh.
Starting with the ground state.
Yeah.
There it's in Euclidean it corresponds to rotation.
In Euclidean, it's a rotation,
Right. So
right? But then when you go to Lorentzian signature, it's a boost, which is a future directed.
okay.
Right. So for example, a thing that you might want to rule out, like if you think about a global thermal state that has a time translation as its modular flow, the kind of question you're asking is why doesn't there exist a state with a spatial translation as its modular flow?
Mhm.
Right? You know, it can be actually a bit tricky to think about the physical principles that are going to stop this thing from happening. So the proof of this theorem uses a technology called microlocal analysis. It is a really, really beautiful technology that I certainly will not have time to talk about in this talk. The big picture of microlocal analysis, if you haven't encountered it, is that its role in life is to help you think about analyticity in curved spacetime, to help you think about the analytic structure of correlation functions in curved spacetime. At least that's one of its roles in life. So if you ever have looked at the old axiomatic QFT literature from like the 70s, if you ever read Streeter and Whiteman as bedtime reading or something like that, then you might have discovered that the way that they prove all of their theorems, CPT spin statistics, involves manipulating the analytic structure of correlation functions in Minkowski spacetime. Microlocal analysis lets you do that in curved spacetime. That's the big picture. The general kind of statement that we're able to make for theorem 2 is that local modular flow must be future directed, ... in any state whose analytic structure is locally like that of the Minkowski vacuum. The microlocal analysis conditions let you make very precise what you mean by analytic structure looking locally like that of the Minkowski vacuum. But because that's the flavor of the proof, for the purpose of this talk, I'm just going to tell you how the proof works for the Minkowski vacuum, and then I'll comment a little bit on the generalization. But it's, it really just involves applying some technical tools to the thing that I'm going to explain now. All right. So we're going to look for a contradiction. We're going to assume that there is a point in spacetime where modular flow is local but not future directed. So for example, this point X has a little space-like vector field going near it. And let's assume that we're the vector field of a modular flow. Right? We're going to pick a point that's null separated. And it's going to have the property that if we do modular flow a little bit in the forwards direction, these points become space-like separated. And if I do it a little bit in the backwards direction, they become time-like separated. So what we're going to do is we're going to draw an interesting conclusion by comparing modular flow, which is some special fancy notion of energy associated with the state, with the global time evolution that we have for free because we live in Minkowski spacetime in this example. And the way we're going to do that is we're going to put a field at X, and we're going to put a field at Y, and we're going to consider a correlation function where we do a little bit of modular flow to the field at X and a little bit of global time evolution to the field at Y. So that's this correlation function F that I've expressed here. Or if I chose to order these fields in the opposite direction, I would have this different correlation function G. And the thing we're going to do is we're going to make the global Hamiltonian and the modular Hamiltonian play against each other in a way that causes a contradiction. Now, one thing you know is that because of microcausality, there's going to be some portion of the ST plane where these two correlators agree. Because if I do, a combined modular and global time evolution in such a way that these points are space-like separated, these two correlators are going to be exactly the same. That's what microcausality gives us. I've just drawn for you what that portion looks like. I mean, you can sort of see if I make S a little bit positive, that's like taking X to be space-like. then I'm gonna have a little wiggle room in T while these points remain space-like separated. You know, that's the kind of argument that gives you this. You should think that you have some ST plane, and you have these two correlation functions which live on this plane, and a priori they're independent, but they agree on this domain. Now the cool thing is that these correlation functions also admit certain analytic continuations to complex values of S and T. You're gonna get an analytic continuation in S because of this KMS condition we talked about before. That's the key special feature of modular flow. And you're gonna get an analytic continuation in T, which has to do with the fact that the global energy is bounded from below. And so you can do some analytic continuation to positive imaginary T. Okay. So you have to think about what this actually looks like, but I've drawn a picture for you. So I took this ST plane that I had before, and I made it the real S, real T plane. And now I'm thinking about this as living in some higher dimensional complex space. So there's like a secret plane hidden inside every point, which is where the imaginary directions live. And if you think about what the directions of analytic continuation give you, you find that this one of these correlators can be continued into the imaginary second quadrant, and one of them into the imaginary fourth quadrant. And in most places on this plane, those functions are going to meet discontinuously. So this is like some high dimension analytic function that has branch discontinuities as it crosses the real plane. But there is a particular domain where these things meet continuously. So I want to encourage you to think of this now no longer as two different functions, but just as some funny higher dimensional analytic function defined on a domain with some branch discontinuities. Okay? And once you understand this, you can use some very, very powerful techniques from complex analysis to show that the locus of branch discontinuities isn't as severe as you initially thought. This technique goes by the name of envelopes of holomorphy. Above one complex dimension, analytic functions behave very differently than in one complex dimension. There exist regions in two complex dimensions for which every holomorphic function can automatically be continued to a bigger domain. And the domain we just drew, this sort of like imaginary second quadrant, imaginary fourth quadrant, blah, 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 is one of these things. And I can draw for you the bigger domain. It looks like this. All I did was I extended the domain of continuity. Right? I extended the portion of the real plane where these two things meet continuously. And there's a very interesting sort of mathematical theorem for why this works. I'll explain it later to anyone who's curious. But you just sort of, black box this theorem from higher dimensional complex analysis, and you get that these correlators, which naively you thought agreed on a pretty small domain, in fact agree on a much larger domain than you might have expected. In particular, they agree for t equals 0 and s both positive and negative. Previously, they only agreed for s positive. So if we look back at this picture, what we find is that the vacuum expectation value of this commutator is going to be 0, not just when the points are space-like separated, but when the points are a little bit time-like separated. On its own, that isn't a contradiction, but you can repeat this argument not just for the vacuum, but for a dense set of well-behaved excitations of the vacuum. And you get an operator equation telling you that these fields, which are only supposed to commute at space-like separation, in fact commute at time-like separation as well. Was there a question? So this is a contradiction, and it proves theorem 2. I don't expect everyone to have followed exactly the details of this derivation, but let me just say, the big picture here is that analytic continuation is an extremely powerful tool because analytic functions are so highly constrained. For the modular flow, we had a special analytic continuation via KMS. For Minkowski time evolution, we had a special analytic continuation via positivity of energy. And if we assumed that these things were too different, one of them went to the future and one of them went to the side, then they were just too strong taken together, and they trivialized the entire theory. So the conclusion you can draw from this is that local modular flow in the vacuum must be future directed. And in fact, you can draw the same conclusion for a general class of states that have the same analytic structure as the vacuum. We could talk about later if anyone's interested. But that's the content of this theory.
Does that class of states include Hadamard states or?
It includes Hadamard states on analytic spacetimes, but not on smooth spacetimes. There's an interesting thing there that, yeah, I think there's a better version of this theorem that could be proved with assumptions that I could control in more settings, but I don't know how to do it for reasons that I could tell you later. Okay. So the light summary so far is that I started by telling you local modular flow was the right tool to generalize the Unruh effect. I told you that it was conceptually interesting for understanding the structure of QFT and practically interesting in applications. But then I told you that the scattered nature of the existing applications makes it valuable to understand the limitations of the technology. And one thing that we showed in this paper was that the scope of these techniques is strongly limited by space-time structure. So this brings me back to Emil's question from before. Well, is this a disappointment? You know, are you just sort of like telling us that the examples we already had is all there is? And maybe you could look at it that way. But I think there are two open questions that are quite interesting. The first one is that I want to note that there are things that satisfy these two theorems that are not in the existing literature of examples. But in those cases, I don't have constructions, right? I have constraints like necessary conditions, but not sufficient ones. So the first interesting question to ask is, are converse results true? If you hand me a spacetime with a vector field satisfying theorems 1 and 2, can you construct a state that has that field as its modular flow? It's very hard to do this in interacting theories because in a general curved spacetime, you don't have control over the path integral. And really the only tool you have for constructing states in interacting theories is the Euclidean path integral. It's the path integral continuation to Euclidean signature. But I do think that progress in free field theory is likely possible using the results of this paper by Bernard Kay and Bob Wald from '91. In fact, Gautam Satyashanchan and I are in an argument about whether it's trivial using the results of this paper. He thinks it's trivial, I think it's easy. So look for progress on that. Okay, so the second question, which I think is the more interesting one, is that I showed you that this local modular flow is very constrained, but in applications, could you get away with something weaker? Now, in this paper, which was about entropy in black holes, the details aren't important for this talk, we showed that for the applications we were considering, we didn't actually need local modular flow. We needed a state whose modular flow was instantaneously local on some slice. And if you think about the way these applications work, you were trying to draw some connection between entropic properties of a state and general features of the QFT stress tensor. Well, if there's some slice on which I can write this operator as an integral of a stress tensor, it doesn't matter if it doesn't look like an integral of a stress tensor on every other slice. And that's the thing that we're currently talking about, is states where no matter which slice you pick, you end up with something that looks like an integral of a stress tensor. So it seems that now that we know that this local stuff, this globally local stuff is seriously constrained, we need to start looking, if we want to make progress, which I think we can do, at states where you have this kind of instantaneously local flow, because these are unconstrained by the present work. I think there's promising, I don't want to make any promises, but I am hopeful that this is going to be possible in free field theory in the near future. This is ongoing work with Gautam Satyashanchan, and I hope to be able to report on it by the end of the year. So, what I told you is that when we wanted to think about thermal behavior, we had this uniqueness theorem which told us that the only tool we could ever use would be modular flow. That means it's an important technology, but insufficiently well understood to determine its limitations. And so things that I think we're expecting to happen recently and in the near future are making progress on technical fronts, for example, in this talk, and on conceptual fronts. For example, this paper that I'll probably talk about a little bit in Bob's group meeting tomorrow, in order to develop new ways to understand quantum fields in curved spacetime and connections with semi-classical gravity. There's a lot to be done. If you're interested, let's talk. Thank you.
Is there hope to derive something like the Tomita-Takesaki theorem for the local sliced version of the algebra, or?
The Tomita-Takesaki theorem governs all of these settings. It governs even the cases where modular flow isn't local anywhere, right? So the special thing in QFT is that there are some specific examples of Tomita-Takesaki theory where you have this local behavior, right? And so now we're trying to broaden our class of what we're looking at in terms of examples. So it's not a Tomita-Takesaki question, it's a QFT question as a particular realization of the Tomita-Takesaki theory.
I guess in some of the applications you mentioned in the beginning, the RG flows and average null energy condition, there it was important that it's local at all times, right?
Well, yeah, I don't actually think it was so important for either of those. I mean, so for the renormalization thing, I don't think it's important at all. Because, for example, what that does is you just look at spheres that exist on a single time slice, and you look at what happens if the sphere is small or if the sphere is very big, but you're still just on a single time slice. So there,
But to connect UV to IR there, don't you need to actually, go the whole way?
No, because you're looking at the vacuum state of the interacting theory and you're probing it at short distances or long distances, but the space-time is static and the state is static. Right? You could think of, the time, the renormalization time has nothing to do with the space-time time. Right? It's like a dilatation scale.
Yeah, but that's why I thought you had to go all the way right from the UV, it coarse grains from UV to IR.
Yes, but I would say those are features of how the correlations of the state are organized on this single time slice. Right? It's subtle because it's information about how these correlations are organized at all scales on this time slice, but I'm not deforming the time slice ever to some curvy wiggly thing. And then for the case of the average null energy condition, in that case, you don't actually need the things to be local everywhere. You need things to be local on a slice. Now, the particular slice that you need them to be local on is the horizon, sort of the Rindler horizon. Or in the case of a general, say, black hole background, you could have the Schwarzschild horizon or something. And so you need to have some like specific surface in that setting, which in that setting is the null surface. And they need to be local on the null surface because you're trying to prove an average null energy condition.
So besides relaxing the requirement of being local, everywhere, and going to this instantaneous locality, are there other parts of this that you're looking at relaxing to see whether those things can be useful? Like, are there any even progress that you can make if you just don't have locality anywhere?
Yes. Okay, there's a long-standing conjecture that has to do with what happens to modular flow as you approach the edge of a region. So maybe it looks completely non-local in most parts of the region, but as you zoom in, sort of see near the bifurcation surface of the region, then what happens? And many people, myself included, believe that no matter what state you're in, modular flow should become approximately local there. And the reason we believe this is because you sort of think that you should be zooming in on the UV effects, and the UV effects should be governed by the vacuum state, where everything is Rindler, Unruh, and so on. But this conjecture is not even understood to the level where we know what kind of approximation we're supposed to look for. So I think that should be understood, but it's probably a ways away.
So are you looking for something where the thermodynamics doesn't need necessarily stationary, right? Which is what you would need to have something that was local on a time slice and then local forever.
Right.
So you're allowed to talk about sort of adiabatic evolution, for instance. So is this sort of the idea that you want to somehow map what's kosher in thermodynamics to what sorts of generalizations of these results you want?
Yes, so I'm doing something extremely brutal. I'm thinking about adiabatic evolution, but of course, how good thermodynamics is depends on the scale of your adiabaticity, right? And so when I was talking, the way you could think about these instantaneously local cases are where I'm doing a sort of a time evolution that is so brutal that it can only be treated adiabatically at a single instant of time. But you might imagine for cases where, so let's suppose that we can show that those things always exist. Then you might start to think about cases where, for example, you have a slowly expanding universe where you have not absolute stationarity, but some adiabaticity. Then perhaps you might have something like an approximate locality that is preserved over some amount of time, and you could be able to use that to draw conclusions that would be interesting.
Maybe related to my question. So I assume the obstruction in the interacting theory is the fact that you can't restrict the algebra to some, time slice in general. So you'd want to talk about some thickened time slice and then,
I would say, you're correct that probably is an obstruction, but the obstruction is more fundamental, which is that you don't even know what tools are available to you when you're trying to study an interacting theory in a curved spacetime. Like you really have very, very little available to you. You have a lot of tools available for studying interacting theory in spacetimes with symmetries, because you can go to Euclidean signature where things make sense at the level of the path integral.
Mhm.
It's very hard to make this work in a Lorentzian spacetime with no symmetries. And I do think, you know, I do think that free field theory has to be our guide there.
Mhm. I see, but if you were in a spacetime with, if you wanted to do, you know, interacting field theory on a spacetime with, some, you know, preferred initial data surface on which well, in the free theory, you had a geometric modular flow, but in the interacting theory, you don't know what to do, you know, like there, the obstruction would just be, I can't restrict.
You're
the-
thinking of like a null initial data
Yeah.
formulation?
Yeah,
Yeah, yes, I agree, that's an obstruction.
I see.
But I would say that's a special case of
Yeah.
the sort of more general thing that you're trying to understand.
Good. Let's thank John again for the talk.